everybody, this is Mrs. Kraus, and this is our second video on the Unit 7 Part 4 notes about pedigrees. We left off our first video talking about how the offspring trait frequencies in a pedigree of a real family don't always match up with the trait frequencies that we predict for a Punnett square. Now we're going to move on to discuss X-linked recessive traits. We've talked about two types of autosomal traits so far, autosomal dominant and autosomal recessive. X-linked traits are different because they are found on the X chromosome, and X-linked recessive traits are controlled by a recessive allele on that X chromosome. An example of an X-linked recessive trait is red-green color blindness. For an X-linked recessive trait, there's going to be more males with these traits than females. That's because males only have one copy of the X chromosome. We can see here that we have two males, two possible male genotypes. An X big A stands for normal, meaning we have normal color vision, and X little a stands for the trait. An example would be red-green color blindness. So because a male only has one copy of the X chromosome, he's going to show whatever allele is on his single X chromosome. So he only needs one copy of that X little a to show the trait. For a female, she needs to receive two copies of that X little a recessive allele in order to show the trait. So it's less likely for a female to have an X-linked recessive trait. There are two phenotypes or two genotypes that can give us a normal female, X big A, or X big A, X little a. Now, this is an example given in your notes of an X-linked recessive pedigree, and in your notes I've explained how I identified the genotypes of each person in the pedigree. I'm also going to go through it with you here. Remember, for an X-linked recessive pedigree, X big A will be normal, and X little a, the recessive allele, codes for the trait. Typically, I follow a series of steps when I'm doing an X-linked recessive pedigree. I write XX's next to my circles because they're females, and females have two X chromosomes. And I write an XY next to my squares because squares are male, and males have an X and a Y chromosome. Once I've written out my XX's and my XY's, I'm going to figure out the A's, big A or little a, that go on my male's X chromosomes first. Once I've done that, I'll be able to go through and on my female's X chromosomes, I can write big A's and little a's. So, once I'd written in my XX's and my XY's, I went through and I wrote my big A's and little a's on my male X chromosomes. I can see that this male is shaded in, meaning that he shows this X-linked recessive trait. So, he has to have an X little a. This male is not shaded in, the dad. So, he has an X big A, meaning he shows the normal trait. For my two females, I know that they have to have at least one big A because they're not shaded in. And the mother up here, I know that her second allele has to be an X little a. I know this because the son always inherits his Y chromosome from his father, and he gets his X chromosome from his mother. For this male to be X little a Y, he had to get the X little a from his mom. For the daughter, I can't really narrow down her genotype. I know she had to get an X big A from her dad. She could get either an X big A or an X little a from her mom. So there are two possible genotypes for her, X big A, or X big A, X little a. So again, the method that I used here was I wrote my XX's for females, my XY's for males. In my next step, I filled in the A's on my male's X chromosomes, and then I filled in the A's on my female's X chromosomes. Sorry, that's the baby. So you have a sample problem where you are identifying the genotypes of people in your X-linked recessive pedigree. And for this pedigree, I'm just going to ask that you do these people in the bottom left-hand corner that I've circled. So remember, we're using X big A to be normal and X little a to be the trait. I would suggest pausing the video here and trying it out on your own first, and then I'll show you how I did it. Okay, now I'm going to show you how I did this pedigree. First, I went through and I put my X's over my circles for my females and XY's over my squares for my males. My next step was to add in my A's on the X chromosomes of my males. So I know that my two unshaded males, numbers 3 and 11, are normal, so they have to have a big A on their X chromosome. I know that my shaded in male, number 9, shows the trait, so he has to have an X little a. Okay, now it's time to fill in the A's on the X chromosomes of my females. So I know that all of my females, 4, 10, and 12, have to have at least one big A so that they're normal. The mother, I know, has to have an X little a because her son is inheriting the Y chromosome from his dad, and he's going to get his X chromosome from his mother. So she has to have an X little a to be able to give to this son, number 9. My two daughters, numbers 10 and 12, we can't really narrow down their genotype. They could have gotten an X big A from each of their parents, or they could have gotten an X big A from their father and an X little a from their mother. So for 10 and 12, they have two possible genotypes, X big A, or X big A, X little a. Our final type of trait is an X-linked dominant trait. So these are traits that are controlled by a dominant allele on the X chromosome. These are pretty rare traits. One of the few examples that I've heard of is a disease called rickets. And with an X-linked dominant trait, because it's controlled by a dominant allele like X big A, it seems to have relatively the same frequency in males and females, because with a female, even if they just get one copy, they will show the trait since it's dominant. Same with a male. If they get one copy, they show the trait. So we're not going to see more males with these traits than females like we do with an X-linked recessive trait. Okay, so here are our possible genotypes and their associated phenotypes. Okay, moving on, this is the pedigree that's shown in your notes, and for each of the people in the pedigree, I explained in your notes how I determined the genotype. And I'm going to explain it to you here as well. So, we know X big A codes for this X-linked dominant trait, and X little a will be normal. Just like with my X-linked recessive traits, I'm going to put my XX's on my circles and my XY's on my squares first. Then I'm going to add in the A's that should go on the X chromosomes of my males. The father is shaded in, so he has to have an X big A, so he shows the trait. The son is not shaded in, so he has to have an X little a because he's normal. And my final step is going to be to put my A's on the X chromosomes of my females. The mother up here is normal. The only genotype she can have to give her that normal phenotype is X little a, X little a. The daughter has to have at least one X big A to show the trait. She must have gotten that from her father. We know her other X chromosome has to have a little a on it because her mother was only able to give her an X little a. Oh my Lord. Okay, now we're going to try a sample problem. Okay, so for this practice problem, remember that X big A stands for the trait and X little a is normal. And we're going to try to figure out the genotypes of these people in the bottom right. So go ahead and pause the video now and try it out. Okay, welcome back. So remember, I always put my x's on my circles and my xy's on my squares. My next step is to add in the a's for the males. So I know this male is X big A because he shows the trait. These two do not show the trait, so they are X little a for normal, numbers 9 and 11. Next, I'm going to fill in the A's on the X chromosomes of my females, so 6, 8, and 10. 6 has to be X little a because she's normal. She doesn't show the trait. 8 and 10 have to have at least one big A because they show the trait. So they must have inherited that from their father, and the only allele they can get from their mother is a little a. So both 8 and 10 have the genotype X big A, X little a. Now, for the types of questions you're going to be asked about pedigrees on a test, you're going to have to be able to fill in the genotypes of people on the pedigree, just like we did in Part B, numbers 4, 8, 13, and 17. I might also ask you to determine if a trait shown in a pedigree shows a recessive or dominant pattern of inheritance. If we see a place in a pedigree where two parents don't show the trait, but they have at least one child who does, we call this skipping generations. So if that happens, the trait has to be recessive, either autosomal recessive or X-linked recessive. If we don't see any places in the pedigree where this happens, where we have two parents without the trait having at least one child who does, we say that there's no skipping of generations and the trait has to be dominant, either autosomal dominant or X-linked dominant. The third thing you might be asked to do is to determine if a trait that's shown in a pedigree shows an autosomal or X-linked pattern of inheritance. If you see approximately the same number of males and females with the trait in the pedigree, so the same number of males and females shaded in, it's probably autosomal. But if you see clearly or significantly more males than females shaded in, that means it's probably an X-linked trait, specifically an X-linked recessive trait. Okay. So here's a sample question. So for number 4, if asked whether this is a dominant or recessive pedigree, I'm going to look for skipping generations. I don't see any places within this pedigree where we have two parents that don't show the trait having a child that does. So since that doesn't happen, we don't see skipping generations. This is probably a dominant pedigree. If we're asked whether this is autosomal or X-linked, we're going to count up the number of males and females with the trait. Looks like I have 1, 2, 3 males and 1, 2, 3 females. So this is an autosomal trait since we have approximately the same, or exactly the same number of males and females with the trait. Okay, so I've written that here. Again, this is dominant because there's no skipping generations, and autosomal because we have the same number of males and females with the trait. For this one, I do see skipping generations. Here I see two parents without the trait having at least one child, in fact 2 that do show the trait. So we would say this is skipping generations and therefore is recessive. And I see that we have 2 females and 1 male with the trait. Because we don't show significantly or clearly more males with the trait than females, we're going to conclude that this is autosomal. And then my last one, I do see places down here, here, and even with these 2 parents where 2 parents that don't have the trait have at least one child that does show the trait. Because of that, we would say this is skipping generations and is therefore recessive. Also, I see that there are 4 males with the trait and 0 females. So I would say that this is X-linked as a result. More males than females. Okay, this is the end of the second video. The third one will probably only take a couple minutes.